Hello everybody and welcome back to this introductory course on machine learning. You've made it through Unit 1 and Unit 2 and now it's time for Unit 3 on unsupervised learning. This is the first video of Unit 3 and it's simply going to cover an introduction to unsupervised learning, kind of lay the foundation for going into more detail and different methods later. But for now, let's take a quick look at the unit overview so we can understand what we are going to be doing over the course of the next few videos. Alright, so this is just video 1 and it's going to be a quick introduction to unsupervised learning. This entire unit is actually going to be a little bit quicker than especially Unit 2, which was on supervised learning, simply because unsupervised learning is less common and has less stuff to cover than supervised learning. So, video 1, quick introduction. Video 2 is going to cover association rules, and with that, market basket analysis, and we'll talk about what that means. Video 3 is on clustering methods, different clustering algorithms, especially k-means clustering. That's the most popular method of cluster analysis. And then video 4 actually isn't on unsupervised learning. This is going to be on reinforcement learning, which is really a third alternative to supervised and unsupervised learning. So since we aren't going to have our own unit on reinforcement learning, we're going to cover the basics of that in this fourth video because it kind of falls into line with this unsupervised learning. But we'll talk about how that's similar and how that differs in that video, as well as some of the different elements of reinforcement learning. All right, so let's get started with this video, and that is the introduction to unsupervised learning. So what is unsupervised learning? To understand that, we need to compare and contrast it to supervised learning, which we explored in the previous videos. And supervised learning was concerned with predicting the values of one or more outputs or response variables for a given set of input or predictor variables. So the predictions were based on the training sample of previously solved cases, and the joint values of all the variables are known. So this is called supervised learning, or you might hear learning with a teacher. In this video, we'll address the alternative, which is unsupervised learning, or referred to learning without a teacher. And in this case, one has a set of observations of a random vector with a joint probability density, and the goal is to directly infer the properties of this probability density without the help of a supervisor or teacher providing correct answers or degree of error for each observation. So you see this probability formula here. We've got the probability of x and y, which is dependent on the probability of y given that we have x, and simply the probability distribution of x. Supervised learning was concerned primarily with this probability of y given that we have x. In unsupervised learning, we're going to be strictly looking at the probability density for our inputs x, because we don't really have an output y. We only have one set of inputs x, and we want to infer the properties about that output probability density. So again, this is trying to gain knowledge from our data. So what are some of the challenges of unsupervised learning? Well, we often have very high dimensional objects in unsupervised learning. So for example, you could use unsupervised learning to do what's called market basket analysis, which is to look at the different transactions or products being bought by customers at a supermarket. And so the input is going to be every single available item in that supermarket. So some stores, maybe Walmart, are going to have tens of thousands of items. So our inputs here are going to be substantially larger than our previous cases. Another challenge would be that the properties of interest are much more complicated than simple location estimates. So we are trying to extract different features from this output probability distribution, and some of those features can be pretty complicated mathematically, and they're not quite as simple as a prediction or location estimate like we've done with supervised learning in the past. Another challenge is that it's fairly subjective. We don't really have a clear measure of success. When we're trying to do something like cluster analysis and form different clusters of similar data, it's hard to say exactly when we are successful. So the output of these models are often subjective in that they have no clear defined measure of success. But there are some benefits to unsupervised learning. There's no conditional variables. So I mentioned in the first slide that there isn't really an X and Y, there's just X. And X represents all of the variables under consideration. Our inputs aren't dependent on an output. Our output isn't dependent on an input. We're only looking at one input variable and the relationship among itself, and it's not conditional on other variables. So that makes our problem simpler in a lot of cases. Alternatively to that, in unsupervised learning, we don't need labeled data. Remember, we don't have an output that we're expecting, which means all we need is the input information, and that can be collected from, like in this sentence here, it says lab instrument or a computer, and it doesn't require this outside intervention to tell the computer what is actually going on. So we've talked about previous examples such as recognizing handwritten digits. Somebody had to go through and look at each image and say, all right, this is a 2, this is a 6, this is a 7, so that the computer could then learn from those positive and negative examples. In unsupervised learning, we don't need to do that step, and so the data is much more accessible. It's very easy to get unlabeled data. It's much more difficult to get labeled data in industry. So unsupervised learning ends up being used in cases when we don't actually have that labeled data. All right, so what are some common methods of unsupervised learning and what are they used for? Well, the first method would be non-parametric methods, and these are very beneficial for low-dimensional problems. So non-parametric is easiest to understood by covering what parametric means, and parametric means is just that we're assuming that the sample is drawn from some distribution that obeys a known model, for example, like a Gaussian distribution. And so this approach is advantageous because it's defined up to a small number of parameters, such as mean and variance, that are the sufficient statistics of the distribution, and once those parameters are estimated from the sample, the whole distribution is known. So in non-parametric methods, we don't make an assumption of that Gaussian model or an assumption of another type of distribution, and we attempt to solve it without that information going in. There's also the alternative, and this is really the parametric methods, and this is the global methods such as Gaussian mixtures or simple descriptive statistics. So a Gaussian mixture is actually going to be a multiple different groups under Gaussian distributions that can be described individually by Gaussian models. But the global methods, you're going to make some more assumptions, you're going to have more implicit bias than in the non-parametric methods, and sometimes that bias can be a means of error. So it's not always good to assume that the data is going to fit these global models such as Gaussian distributions, because we don't always know that for sure with our input data. Another one is cluster analysis, and this is actually going to be the subject of video 3. So cluster analysis is simply trying to group objects or input data into similar clusters. And so in cluster analysis, we're going to talk about similarity and dissimilarity and how we define that in a lot of different scenarios. Cluster analysis is actually going to be probably one of the most common unsupervised learning methods. Also with that, we have association rules, and this is going to be the topic of video 2. Association rules are looking for dependencies amongst different variables. And again, this is going to be used in market basket analysis, where we're looking at the transactions in a supermarket, let's say, and trying to come up with conclusions like, if a customer buys this product X, they're also going to like this product Y. And based on that information, we can change our marketing schemes or advertisements to reflect those associations. So these are some of the common methods. We're going to cover cluster analysis and association rules in more detail. Non-parametric methods and global methods we're going to mention and then kind of leave aside simply because we don't have time to dive into all of these different topics in depth in this introductory course. But it's still good to know that they are available and out there because they are beneficial in some scenarios, like the non-parametric methods in low-dimensional problems. However, when we start to get thousands or tens of thousands of dimensions based on simply on the number of inputs that we have, that is when we're going to be using things like cluster analysis and association rules, which we will talk about more in the later videos. All right, so we mentioned the measures of success in unsupervised learning. In unsupervised learning, we don't really have a clear measure of success. It's very subjective. In the supervised learning videos, we talked about clearly defined metrics such as expected loss, empirical error. We mentioned the residual sum of squares. These things can all be used to lead our model in the right direction and teach it what we want it to learn. However, in unsupervised learning, there isn't that clear direct measure of success. We'll talk about later in k-means clustering how we can use something such as Euclidean distance to produce a measure of similarity or dissimilarity. However, that is going to vary depending on the methods that we employ. So it's important to keep in mind that unsupervised learning doesn't have a clear measure of success. However, it is going to be very beneficial if we're trying to extract features or knowledge about our input data and learn about the output probability distribution or just the probability distribution of the data that we have and extract that distribution so that we can use it for future analysis. So this is an introduction to unsupervised learning. We're going to dive deeper into cluster analysis and in the next video, association rules, so we can see how we're actually going to employ this type of machine learning. Thanks for listening. Very useful algorithm, and it's generally going to be the one you use if you're looking for more than just 2 items in each item set. So this gets used all the time and is going to be the most common application of association rules. So we also need to talk about hidden variables, because it should be kept in mind that a rule like if X then Y does not need to imply causality, but just an association. In a problem, there may also be hidden variables whose values are never known through evidence. So the advantage of using hidden variables is that the dependency structure can be more easily defined. So let's talk about this through an example. If we were looking at a problem of basket analysis and we want to find the dependency among items sold, we could have a dependency among baby food, diapers, and milk, and that the customer buying one of these is very much more likely to buy the other 2. So instead of representing dependencies among these 3, we may designate a hidden node, such as a baby at home, as the hidden cause of the consumption of these 3 items. When there are hidden nodes, their values are going to be estimated given the values of observed nodes and then filled in. So this is really going to be the only time we touch on hidden variables, but it's just really important to know that these association rules do not imply causality. So buying milk does not cause you to buy more bananas. They are simply associated together. So let's take a look at a basket analysis example, and we're going to do so by considering the following transactions. So we only have 8 transactions here, so very small input set. However, we have a variety of different products being bought. We are going to look at the dependency between beer and apples and see if we can come up with anything for that. So we see those occurring together in a fair amount of these transactions. So we might think that there would be a connection between the 2. So let's go ahead and calculate our 3 measures, being support and confidence and lift, and see if we can actually mathematically show an association between these 2 items. So we're going to start with the support, and this is going to be the first step in learning the association between apples and beer. The support is simply going to be for the support for apples, the probability of apples. There were, if we look back, 4 transactions out of a total of 8 where we got apples. So this is just going to be a support of 0.5. 0.5, it's fairly significant, so we're going to go ahead and say that there is statistical significance behind this, so it's worth pursuing. And then we move to the confidence. So the confidence is going to be the support of apples and beer divided by the support of just apples alone. And so to calculate this, we see that 3 out of 8 times apples and beer are bought together. and then we're going to divide that by 1/2, just the support of apples alone, and so we get 75% confidence. So not only is this statistically significant, but there is strong strength between these two items. But let's move on. Let's look at the lift. So this is going to be calculated as such. We have the support of the apples and beer divided by the support of apples and beer alone. So this is going to be looking for a dependency between these objects by taking into consideration the probability distributions of simply beer and apple occurring. So this is calculated as such. Again, we have 3 out of 8 times apple and beer are bought together. 4 out of 8 times the apples are bought, and then 6 out of 8 times actually beer is bought. And this ends up coming out exactly equal to 1. So unfortunately, despite the statistical significance and the strength of the rule, there is no dependency between these items that we can see, at least in these 8 transactions. So buying apples does not make you more likely to buy beer, and buying beer does not make it more likely for you to buy apples. So unfortunately, no dependency here, but still useful data. And so that's just a quick easy example of an association rule. The a priori algorithm is going to sort through your entire database, all of your transaction data, and try to look for some of these rules. And then you can use those in your marketing. So this is association rules in a nutshell. Just a quick video to introduce the topic. And these are used almost all the time in different consumerist applications where the company wants to use it for stocking shelves or cross-marketing, sales promotions. So really good to understand association rules. Actually very easily implemented because you're not going to develop the new algorithms yourself. You're simply going to use a priori algorithm. However, you're going to set your own support and confidence levels that you want to look for in your rules. So that's association rules. Our next video is going to be on cluster analysis. And cluster analysis is actually going to be the bulk of unsupervised learning, in my opinion. And so we're going to look at some of the math behind cluster analysis and some of the applications as well. So thanks for listening, and I'll talk to you guys soon. Hello and welcome back. This is video 3 of Unit 3, and it's going to cover cluster analysis. And once again, this is presented by EDU Onyx. Cluster analysis, very important in industry. This is going to be arguably the most popular or primary application of unsupervised learning. Thus, we are going to spend a video talking about it and how it is implemented. So this is an important video, probably the most important one in this unit on unsupervised learning because it's going to be arguably what you're most likely to use in the future. So pay attention and let's dive right in. So cluster analysis, or also called data segmentation, has a variety of goals, and all of these goals relate to grouping or segmenting a collection of objects into subsets or clusters such that those within each cluster are going to be more closely related to one another than objects assigned to different clusters. So an object can be described by a set of measurements or by its relation to other objects. And cluster analysis is also used to form descriptive statistics to ascertain whether or not the data consists of a set of distinct subgroups, each group representing objects with substantially different properties. So this goal requires an assessment of the degree of difference between the objects assigned to the respective clusters. So here on the right, you see an example of cluster analysis, and this is just simulated data, but it was randomly distributed, and here it is segmented into 3 distinct clusters. So you see our green dots up at the top, then the blue in the middle, and the orange in the bottom. Looking at this data, if it was all just black points, it would be hard to say that there were 3 distinct points, but this is an example of using k-means clustering, where we're absolutely able to show mathematically that they can be separated into these distinct groups. So central to all of these goals, or goals of cluster analysis, is the notion of the degree of similarity, or probably more often than not, you're going to hear this referred to as dissimilarity. And this is the dissimilarity between the individual objects being clustered. So a clustering method attempts to group the objects based on the definition of similarity supplied to it. So this can only come from subject matter considerations. So our definition of similarity is going to depend on the data that we're looking at. In video 2, when we did our project, we made sure that we did several data visualization steps before actually applying an algorithm so that we could understand the data that we're looking at. In machine learning, once again, it's very important that you understand your underlying data so that you can pick the most appropriate model, or in this case, the most appropriate measure of similarity. So this situation is somewhat similar to the specification of a loss or a cost function in prediction problems like the ones we talked about in our Unit 2 on supervised learning. So now that we have this definition of similarity out there, we can update our goal of these cluster analysis algorithms, and that goal being to partition the observations into groups so that the pairwise dissimilarities between those assigned to the same cluster tend to be smaller than those in different clusters. So here is our official goal, complete with our application of dissimilarities. So this is what we're looking for in cluster analysis. So let's take a look at a couple of different algorithms that can be used to accomplish this goal. So these are the three main types of clustering algorithms. The first one being the combinatorial algorithms. So in these algorithms, we are going to work directly on the observed data with no direct reference to an underlying probability model. So we're not going to assume that the distribution is Gaussian. This would be considered perhaps a non-parametric approach. We talked about that in our intro video, non-parametric versus parametric, where we do assume such distributions such as Gaussian. And this is going to be the opposite of that. No underlying assumptions. We're going to work directly on the observed data. The next one is mixture modeling. So this is going to be the parametric approach, in that it supposes that the data is a sample from some population described by a probability density function. So this density function is characterized by a parameterized model taken to be a mixture of component density functions. So each component density describes one of the clusters. This model is then fit to the data by maximizing the likelihood or corresponding Bayesian approaches. So in this approach, we're going to have different clusters, and we're going to assume that each cluster has its own probability distribution, such as a Gaussian distribution or other similar models such as that. And we're going to separate it into distinct clusters where each cluster has that distribution. You don't have to use just Gaussian distributions. One cluster could be a Gaussian, whereas another one could have like a Bernoulli distribution or some other type of distribution. So that's mixture modeling, and our third one is going to be called mode seeking. So mode seekers take a non-parametric perspective, and they attempt to directly estimate distinct modes of the probability density function. So observations closest to each respective mode then define the individual clusters. So we've previously touched on mode hunting or bump hunting, you might hear, and this is the third type of clustering algorithm. And mode seeking, we're not going to touch on it very much, but it does come up, so it's important to know about. We're going to talk exclusively about k-means clustering, and this is because it is by far the most popular combinatorial algorithm, which is by far the most common type of clustering algorithm. So more often than not, you're going to see k-means clustering. So let's go ahead and dive right into that, explain it more fully, look at some of the math behind it, and as well, an example of k-means clustering being used. All right, so here's k-means clustering, and the k-means algorithm is one of the most popular iterative descent clustering methods. It is intended for situations in which all of the variables are of the quantitative type. So we have numerical values, and then the dissimilarity measure is often chosen to be the Euclidean distance. So this example that we're going to look at is going to be a two-dimensional example, so it's very easy for us to use Euclidean distance. However, there might be the case where we have higher dimensions, and then you have to do dimensionality reductions in order to apply Euclidean distance or something like that. In these examples, The K here in K-means clustering is going to refer to the numbers of clusters that we choose, and this is a value that's predefined. So we can pick the number of clusters. We might not know how many clusters there should be, and then we have to do like a guess and check type method where we maybe use a K-means method with a variety of different cluster numbers, and then choose the one which has the best output. So let's keep going and take a look at the actual algorithm. So here is K-means clustering, and so we're going to start with a three-step process. And before this begins, each of these clusters is going to be initialized with random centers. So we're randomly going to pick points throughout our distribution of inputs and define them as our cluster centers so that we have something to start on and iterate on. And then from there, each data point is going to be assigned to the closest cluster center in Euclidean distance, and that's going to be defined as such. So then step 2, each cluster center is going to be updated and is going to be replaced by the coordinate-wise average of all the data points that are closest to it. So this is why it doesn't matter that we start with random weights. And in fact, it's actually beneficial to start with random weights because the K-means clustering algorithm is not guaranteed to find a global minimum. So in fact, when you're using this method, you often want to start with several different random initiation points, there we go, and go from there and see which one finds the best minimum, because again, we're not guaranteed to find the global minimum. And so our last part of this algorithm is just to repeat these steps, finding the closest center and then updating the center average until the assignments do not change and all of the points are into their respective clusters. So let's take look at an example of this because it actually will help clarify how this works much better. So this image is a K-means example, and in the upper left you see our data. This is just a random distribution, randomly generated. All the points are in black, so we have no clusters yet. Step 1, we're going to assign them to random clusters. So that's all interspersed. For this example, we're picking 3 clusters, and then in our top right example, we randomly initialize our cluster centers. So we have 3 cluster centers. These are placed pretty much exclusively right in the middle with some slight differences. And then we're going to start iterating over this data. So in the bottom left, each data point is assigned to the cluster of the closest center in Euclidean distance. So we have our 3 separate clusters now. You see we have our purple or pink in the bottom, our green and our orange as defined by the closest center. In the middle bottom, we update the location of that cluster center. So now you see it's moved pretty dramatically outwards, and we continue doing that until our assignments between clusters don't change. So if you look at the middle bottom versus the right bottom image here, you'll see that the pink actually loses many of the data points on the right, and those end up being assigned to the green cluster, as well as some of the bottom points in the orange cluster end up being assigned later to our pink or green clusters. So this algorithm iterates over itself until once again we find that local minimum. It's important to remember that it's not a global minimum, so actually this process should be repeated using different initial parameters each time so that we can try to search for the best local minimum. It might be that this is the global minimum, but it's important to try to start in different scenarios so that we can check that. And it's also, again, important to start with a different number of clusters. We should probably check 2 clusters because these could probably be better separated into 2 clusters. We can check with 3 or 4, maybe even more clusters. And this is, again, one of the main reasons why it's really important that we understand our underlying data. So we have data subject matter considerations to take into account when we're applying these algorithms. So that is K-means clustering in a nutshell. Here is a quick summary. Cluster analysis attempts to group or segment a collection of objects into subsets or clusters, such that those within each cluster are more closely related to one another than the objects assigned to different clusters. So this is the goal and approach of clustering analysis. And then more specifically, k-means clustering is the most popular combinatorial algorithm for clustering and uses an iterative descent model to cluster quantitative variables using Euclidean distance as the dissimilarity measure. So those are the main takeaways from this video. We're actually going to look at a live coding example of k-means clustering. So that'll be exciting. That'll be the project for this unit. But before that, actually in the next video, we're going to talk about reinforcement learning. So once again, reinforcement learning isn't necessarily unsupervised learning, but it's not big enough to have a unit of its own. So we're going to talk about it here and now. And reinforcement learning is actually one of the most exciting parts of machine learning research today, at least in my opinion. Reinforcement learning is kind of what's assumed when we're talking about things such as artificial intelligence. It's based off psychology and reward systems, but we'll talk about that all in the next video, so that'll be exciting, and keep listening. Thanks. Welcome back. This is the fourth and final video of Unit 3, and it is going to cover reinforcement learning. So reinforcement learning, once again, is a third alternative. It's not supervised learning, it's not unsupervised learning, but we're going to explain it here and now and talk about it because this is one of the coolest parts of machine learning and is actually going to be the focal point for our final project in this class. So it's important that we cover it and understand how and why it works. So let's get started. So here's just a quick introduction, and again, this is just showing that machine learning as a whole is comprised of supervised learning and unsupervised learning. Nobody really wants to throw reinforcement learning into these two categories, one of these two categories, because it doesn't have really the same characteristics as the other two. So in reinforcement learning, we don't have a supervisor, only reward. So we don't have that output that's telling us this is a positive example or a negative example. Furthermore, the feedback is delayed. We might have to make some choices in the here and now, and we're not going to understand if those were good or bad choices later on. Next, time really matters in reinforcement learning applications. Well, most of reinforcement learning applications. So we're going to have to consider time as well as the simple results or output of our algorithm. And finally, the agent's actions affect the subsequent data it receives. So depending on what our algorithm does, the environment or the input space is going to change. So that is definitely different than our supervised or unsupervised learning examples where our input data was very static. It was set beforehand, and then we applied our algorithm to it. So some examples of reinforcement learning would to be defeat the world champion at backgammon or chess, or to make an investment portfolio, control a power station, maybe make a robot walk, or play an Atari game. So these are some very cool applications of machine learning. They're what come up in articles more often than the other machine learning techniques. It's also one of the newer machine learning approaches and has some of the coolest applications, I think, in my opinion. In Unit 4, when we talk about neural networks and deep learning, we are going to continue talking about reinforcement learning because it is used in conjunction with deep learning networks a lot of the time. But let's keep diving into the specifics. So the goal of reinforcement learning is to learn the best policy, that is, the sequence of actions that maximize our total reward. So we'll go in, we'll define some of these words like policy or agent in a bit here. But for now, it's important to understand that the overarching approach is to not make the best choice or action at each individual step. It's to make the best policy, which is going to be a sequence of actions taken by the agent that maximizes the total reward. So, for example, if we're playing the game of chess, we don't necessarily want to just make a good move at every single instant. We want to win the game. So if we build a machine that learns to play chess, in this case, we cannot use a supervised learner for two reasons. First, it would be very costly to have a teacher that will take us through many games and indicate the best move for each position and situation. And then second, in many cases, there is no such thing as the best move, as I just mentioned. So the goodness of a move depends on the moves that follow. So that's very different than other machine learning applications we've looked at. A single move does not count. A sequence of moves is good if after playing them, we win the game. So winning the game is going to be our reward here. And the only feedback is at the end of the game when we win or lose the game. So our algorithm is going to have to make choices not knowing or not getting immediate feedback on those choices. Another example would be a robot in a maze. So the robot can move in one of 4 compass directions and should make a sequence of movements to reach the exit. So as long as the robot is in the maze, there is no feedback, and the robot tries many moves until it reaches the exit, and only then does it get a reward. So in this case, there is no opponent, but we can have a preference for shorter trajectories, implying that in this case, we play against time, so we have time considerations in this example as well. So we had a lot of terms in those kind of examples and definitions, so let's help with that and define some of our elements of reinforcement learning and actually define some of these terms. So in reinforcement learning, we have what's called the agent, and the agent is simply going to be the decision maker which performs the learning. So the agent, again, is the algorithm that we are trying to teach, and the agent interacts with an environment, that is the area, space, or game that the agent is in. For example, in chess, the game player would be the agent, and then the board is the environment. And specifically, the board will have what's called a state. So that is the current environment. And the environment is in a certain state that is one of a set of possible states. So, for example, the position of the robot in our maze, or the current position of every piece on the chessboard would be good examples of state. Interpreting that state, our agent can then take what's called an action. So actions are possible moves by the agents, such as a legal move in chess, or the possible directions without hitting the wall for our robot in the maze. Based off that action, our agent is going to get a reward. So this is feedback on our sequence of actions. Generally, this is only received when the completed sequence is carried out. So, for example, we get +1 if we won the chess game, -1 if we lost. So we want to maximize our reward, so we want to win as many games as possible. And the learning agent learns the best sequence of actions to solve a problem, where best is going to be quantified as the sequence of actions that has the maximum cumulative reward. So it's really going to be dependent in these scenarios how we define our reward. Some other terms that you might want to know are episode or trial, and these are going to be the sequence of actions from start to the terminal state. So we have some initial state that begins our episode, and then after the episode, all our sequence of actions has been undertaken. And then finally, policy, and that's going to define the action to be taken by the agent in any given state. And policy is really what we care about. It's not each individual action, it's how we respond to the environment in any given state, because that is going to define our sequence of actions, which helps us reach our goal. So this is the general setup. These are the elements of reinforcement learning. Let's dive into the environment in a little bit more detail. So the environment can really have 2 different scenarios. We can have fully observable environments. So this is going to be when the agent directly observes the environment state. And this is known as the Markov decision process, or MDP. And fully observable environments are when the agent has complete access, complete knowledge of the environment that it's in. So maybe it knows all of the rules of the game that it's playing, or it understands the complete map of the maze that it's trying to solve. In other scenarios, you're going to have partially observable environments, and the agent indirectly observes the environment state. So, for example, maybe we have a robot that's trying to navigate through our maze, but the robot only has a camera and doesn't know its absolute location. So the environment or the state is going to be dependent on the location of the robot, but the robot doesn't understand that. It doesn't know its exact location. So this is going to be partially observable. So the agent state does not equal the environment state. In this is known as a partially observable Markov decision process, or POMDP. And once again, the agent must construct its own state representation because it only has partial information here. And this state representation that the agent creates is going to be based on the complete history of observations that it's made, and as well as beliefs of the environment state. So it's going to try to make future predictions off of prior information because it doesn't know the entire environment. But we'll take a look at some of these a little bit later on. But for now, let's explain the agent in a little bit more detail. So the agent may contain one or more of the following components. The first component being the policy. And the policy is simply going to be the agent's behavior function. So this would be a map from state to action. So given a certain state, maybe the position of chess pieces on the board, we're going to perform the particular action or this move. The next component would be a value function. So how good is each state and or action? So these value functions are going to take into account future rewards. So we're going to try to make a prediction of future rewards and move in the direction or take the action that maximizes our value. And ultimately, this is going to help us develop a policy. Finally, we might have a model in our agent, and this is going to be the agent's representation of the environment. So a model is going to help us because we can predict what the environment will do next. So you see both a value function and a model are going to help our agent form predictions. In the last slide, we talked about a partially observable environment and how an agent would create its own state representation based off beliefs on its environment state. A value function and a model are going to help that agent create these beliefs. So once again, an agent doesn't have to have all of these components. It certainly doesn't need to have a model. However, these are different aspects of an agent that may help it learn or generalize to new scenarios. So let's use an example to go over this, and we're going to continue using our maze example. So here we have the environment. We have an initial state, the start location, and we have a final state or a goal that we're trying to reach. So we can take any sequence of actions to get there. However, in this scenario, we're going to have some rewards, and we're actually going to get -1 per time step. So we want to take the fewest number of steps possible. Our available actions are going to be to go north, east, south, or west. So we're confined to 4 distinct actions. And the state in this case is going to be the agent's location in our maze. So if we're using policy, this is what a policy might look like. And each little box, an arrow is going to represent the policy for each individual state. So if you look at this upper right image, if our agent was in the very bottom left box, you'd see that he would move to the right, or because this is the ideal direction to move if you are in that particular state. And you can see starting from our initial state, we're simply going to follow the maze along in the shortest available path and reach our goal. Here is an example of a value function. So in this, the numbers are going to represent the value of each state. So it's really valuable to be right next to our goal, but not so valuable to be at the start, and really awful to be stuck down in the bottom left corner of this maze here. So we want to move in a direction where our future actions are going to have a higher reward, so we're going to want to move towards our goal. In the last case, we might have a model. So maybe our agent understands that this is the general route that it should go, but it's important to understand that the model may be imperfect. So in this model, there are a couple wrong moves in there. Maybe it takes a right turn right at the start of this maze, and that's going to be an incorrect model, but in general, this is going to make it to our goal. So these are the 3 different ways that an agent could solve this maze. It could use policy, it could use a value function, and it could use a model, although it may be imperfect. Or it could use a combination of these 3. So let's move on, and we're going to talk about learning and planning a little bit, and how our agent actually can use reinforcement learning or use planning and beliefs about its environment to move forward. So these are the 2 aspects of sequential decision making, and reinforcement again is primarily concerned with sequential decision making. The first is reinforcement learning, second planning. So in reinforcement learning, the environment is initially unknown. This is if you don't have a model, you don't know what you're interacting with. Maybe you're playing an Atari game and you don't know the rules. However, the agent is going to interact with the environment, so we start playing the game and we get feedback from that. Maybe we won, maybe we lost, and generally we're going to improve our policy as we continue to learn. So we're going to get better and better at playing the game, even though we weren't explicitly told the rules. The alternative to that is planning, where the model of the environment would be known, and this could be maybe fully observable or partially observable. So we may know the entirety of the model, we know all the rules and all the best actions. Maybe we only know some of the rules and some of the actions. And then the agent is going to perform computations with its model and use those computations to improve its policy. So this is going to be when our agent is making predictions about the future or forming beliefs about its environment so that it can choose an action that it thinks is going to maximize its reward beforehand. This is very much so planning out its attack instead of just learning by trial and error, such as in the more strict reinforcement learning. So each algorithm is going to use a combination of these two approaches. Most of them are going to do some planning as well as some trial and error. But overall, the goal is going to be to form that policy that results in our maximum reward. So a quick summary of reinforcement learning, because this was just a very brief introduction and very quick. In reinforcement learning, our goal is to learn the best policy or learn the best sequence of actions that maximizes our reward, and our reward is going to be defined in different ways in different examples. And some elements of reinforcement learning, we have the agent, which is the decision maker, and the agent is actually the one performing the learning. We have the environment that the agent interacts with, and this is going to be the current state or space that it's in, state being the current environment, the environment being maybe the rules of the game or the maze that the agent is in. We have actions, which are possible moves by the agent, and we have reward, which is the feedback on our sequence of actions, often coming only at the end of the game. So this is reinforcement learning in a nutshell. Again, we are going to take a look at a reinforcement learning example using the OpenAI Gym environment in Python in our final project. So we're going to help you understand this better by getting your hands dirty and actually programming a deep learning reinforcement algorithm. So stay tuned for that. That's going to be exciting and really help reinforce, pun intended, some of these concepts. Thanks for listening.
Hello everybody and welcome to Unit 3's project. So this is where we actually get to practice our Python programming skills and apply some of the knowledge that we learned in the earlier videos. So in this project, we're going to be developing a k-means clustering algorithm that we're going to use to separate some distinct clusters in simulated data. So once again, this is going to be done in a Jupyter notebook, which uses Python. We're going to be using Python 2.7, and we're going to use the scikit-learn library to implement these different algorithms. If you followed along in my first tutorial that we did in Unit 2, when we were looking at supervised learning, a lot of this should be review, so we're going to go through it pretty quickly. The first review being the use of conda. If you don't have the packages we need installed, it's as easy as typing conda install and then the package that you need. Noting that to do this, you have to have conda in your path variables, but that should already be set up and good to go. For this, I'm going to go to tutorial. And then, so when you're opening a Jupyter notebook, wherever you are in your command prompt is going to be where the notebook opens. So I could actually back all the way out and then open this from my user folder or maybe from documents. Wherever you type Jupyter notebook, that is where it is going to open. So I'm going to open this here in my tutorial folder and we will get this going. So it's going to do its thing and open. It's going to go pretty quickly here, which is nice. Here we go, and I am going to pull this out. All right, so we have an empty folder. I'm going to start a new notebook, picking the kernel again. You probably only have one kernel available. I've got a couple because I've set up a couple of different environments, and that is, again, one of the many benefits of using Conda is that you can generate new environments. All right, so let's give this a title, Unit 3 projects, and we are going to be doing k-means. All right, so to start any programming project, you're going to import the necessary packages. I'm going to do an import sys just so that we can check and make sure. I'm going to do print sys version. It's always good to make sure you're using the version that you think you are. Here we go. Yep, Python 2.7. That's great. That's what we want to use. It's most common in industry. All right, so here are the libraries that we're going to use. We're going to be using, once again, NumPy. And NumPy is used for computational problems in Python. It's very valuable, especially when you're dealing with arrays and vectors like we will be in this machine learning project. The next one is matplotlib. PyPlot is great for visualizing data, so we're going to use it for that. And we're also going to use the scikit-learn library again, specifically the k-means algorithm. So in machine learning, scikit-learn in Python is paramount. This is what you're going to use the majority of the time. So let's go ahead and, again, Shift-Enter to evaluate a cell in Jupyter. Good. All of those are imported and installed. Once again, if you don't have one of these packages installed, although you should if you followed the previous project, it's as simple as going into your command prompt and then typing conda install whatever package you need. All right, so let's go ahead and generate our data, and we are going to use two means here. So first step, making the data that we are going to do the clustering on. We have the advantage in that we are going to create our data. So we're going to have some better understanding of its underlying structure. So to do that, we want to start by generating a couple of different means for our different distributions. And we are going to be doing a random multivariate normal distribution. And I don't want to know all the details, so I'm going to let it generate a random mean here. And we're actually going to do this twice so that we can have two clusters in our distributions, and that will help us actually have data to separate. We could do more than two clusters if we really wanted to, but for the sake of this tutorial, we'll keep it relatively simple and only do the two here. So here's when we're using NumPy to actually generate our random multivariate distribution. And it has these very convenient functions that get used all the time. And it's just going to be, oh, I forgot my covariant matrix. Before we do this, we're going to have to make diagonal covariance. There we go. And so we got to specify this in matrix notation first, so that it can know what type of standard deviation it should be using for these different distributions. So we'll do that now. Here we go. It's as simple as that. So a standard deviation of 100 in both the x and y directions. There we go. Now we can have our covariant matrix here. We're just going to do 100 data points. And we're actually going to do this twice so that we can have both of our distributions here. And this second one's going to be based on our second mean, which I failed to rename up here. So here we go. Two means, two distributions. Let's go ahead and append those together, once again using NumPy, so that we only have one set of data. Here we go. y1, y2. I accidentally put y here. This should be x2. There we go. So our x and our y, we have both of those. And once again, this is a machine learning application, so it's pretty important that we understand our underlying data before we apply our algorithm. So let's go ahead and plot this before we get started using the PyPlot from Matplotlib. And we're going to make these axes equal, so it'll be nice and square. And PLT just show, this will bring up our figure. So let's again shift enter to run this cell, see if we've got everything correct. And we do. All right, so here you see pretty distinct clusters. I'm going to actually move these in a little closer to each other so that they overlap a little bit more. And that way it'll be a little harder for our algorithm. It's not too impressive if our algorithm can separate these two clusters. Those are pretty obvious to see. But let's see if we can get something that overlaps. I like this one a lot. This is perfect. Some of these points in the middle here are pretty ambiguous which cluster it belongs to. So this will be a good set of data for us to apply this k-means algorithm to and see if we can actually separate them out. All right, so let's keep going. We have our data, but first we want to combine it into a NumPy array of just x and y data. And you can do that with the zip. The zip will keep this as coordinate points. So that should be good to go. Yep, there we go. All right, and now we're actually going to be making our k-means model. So this is when we actually start applying the machine learning to this data. And so the scikit-learn library makes this very easy. We can just initiate a k-means model here, and we're going to specify the number of clusters. We have the huge advantage here that we actually know what this number should be. Sometimes you'll have to search for it, but for now, since we know it's actually 2, we're going to try to separate this into 2 clusters. So let's initiate this. There we go. And then what I'm going to do in this next slide, or this next cell, is fit the model to the data. So to do that, again, very easy using this library. Simply fit, and we're going to fit this to our x, our input data here. So let's go ahead and run that. Excellent. So the k-means, the algorithm, automatic. It's going to do 300 iterations here, and looking for 2 clusters, and that is exactly what we want. So it's going to output some different features here. One thing it's going to do is find the centroids, the center of each cluster. And to see those, we can just pull this up using cluster centers here. Again, just a feature of the package. And then it's also will have labels for each individual data point. Which cluster does it belong to? We only have 2 clusters, so these labels are going to be a 0 or 1. So let's print these out so that we can see them, our labels, and then print our centroids. All right, let's see if we've got everything here. Excellent. All right, so we have 2 cluster centers, and here those are x and y data. And here are the labels. And this makes sense just because of the way we created this data. And remember, we appended it to the end, just x1 and x2. So the first half of this data should be from our first mean cluster, and the second half will be from the other one. So you see there's actually some that are classified with the other labels, and that's because of the overlap in the middle. But once again, data visualization, incredibly important. So let's keep going and visualize this data. So colors, we're gonna define a set of colors here. So we're just going to do green, and let's also do red. 2 clusters, so we only need 2 colors. If you end up adding more means, just to see this example with more clusters, you're going to have to add a color here. All right, and then let's iterate over this data and plot it with each iteration. So for I in range, and we're just going to be using the length of x here, so the length of our inputs. So for each input, we're going to do a pie plot, and that is plots, and we are going to want our x data here. So this is going to be x of I of 0. So first input, second input, third input of the x here. And then on the corresponding y value of this right here. And remember, this is a matrix notation, so our first index is 0, our second is 1. All right, and then colors, we'll have this draw from the labels. So it will color it according to whichever cluster it was classified as. Marker size, just make our graph look pretty. Okay, we'll come down here and we'll do a PLT, we'll do a scatter plot. 2 T's in scatter. We're also going to plot our centroids so that we can see where it is picking the center of our clusters. And again, just the x and y data here, 0 and 1. All right, so marker, let's make these actually noticeable so that they stick out from the rest of our data. So do a side, we'll make these pretty big at 150. And Z order, we want these to be in the front so we can see them. All right, once again, plt.show to bring this up. So drum roll here, let's plot this. Here we go. So 2 clusters separating the red on the left, the green on the right, 0 and 1, and we actually have these blue X's here are marking the centroids. So this looks pretty good. It did a pretty good job of separating these into its 2 classes. Another way that we can compare how well this did is by comparing the centroids to the actual means. We've got the unfair advantage of knowing what it should be. And remember, the success of unsupervised learning algorithms is kind of hard to classify. Who gets to dictate if this was a successful clustering algorithm or not? It's harder to say. So the results are semi-subjective, but we can compare it to the actual means since we were the ones that generated the data. So here we go. We have the centroid here, very close to our 429, and then 4026, very close. So it's off by about 1 or 2, but not bad considering the spread of our data and the corresponding characteristics. So that's k-means clustering in a nutshell. If you want to go back, add another mean, please do. 2, 3 extra means and try to separate this into more than just 2 clusters. You're going to have to add a color here, change the number of clusters that you're using in your algorithm. Remember, this is just really straightforward to implement because the scikit-learn library makes using these algorithms very straightforward. Some of the data preparation stuff using NumPy. NumPy is very, very valuable. NumPy gets used in almost all machine learning applications, so getting familiar with NumPy and its capabilities is also very important. So that's k-means clustering. Thank you for participating and listening and following along. We're going to move on to Unit 4, where we get to talk about neural networks and deep learning. So that is going to be equally engaging and just as exciting. So keep listening. Thanks.